Hello, I'm Daniel. Those of you who don't know what this is a picture of, so last week Jared took me to drag me with him to Ireland. And when you're in Ireland, you go to Dublin. And when you're in Dublin, you go visit Guinness. And when you go visit Guinness, you go hunt down William Gossett's plaque while drinking a properly poured pint of Guinness. And so the way my sister puts it, I am Guinness beer in my belly. So who am I? I am a graduate student at Virginia Tech. I work in the Social and Decision Analytics Laboratory in DC. While I am sitting in Blacksburg, Virginia, I sit with the folks in the Network Dynamics and Simulation Science Laboratory. So I do a lot of network-related things. So I get to call myself a computational epidemiologist. So I'm also a software carpentry and data carpentry instructor, where I am the lesson maintainer for the R lessons there for them. And I also am the Arch user repository maintainer for the RStudio desktop preview version. So those of you who use Arch Linux, I just updated after JJ said this morning that there was a preview version, so I made that update. Jared and I have frequent qualms about Linux and Windows. So just to bury the hatchet, I'd like to say Linux, it doesn't really matter what operating system you're on. It's really just a bootloader for RStudio anyway. Or maybe Python as well, yeah. So, and I also work with Jared. So this talk is about testing. And what do you test? Well, you test anything, everything. You test your functions, your data, and your scripts. So those of you who just want to go to sleep, or essentially I would be talking about, I list 4, but I talked about 3. RUnit, test that and validate by the respective people who maintain them. Data check is on the list because this is a package that other people in my lab work use, but I won't be really going over it in this talk. So testing functions. I'm sort of stealing this from the software carpentry examples, but one of their old Python 2 versions uses temperature conversion as their example. And so we can define a function that takes one variable, temperature, and it performs a Fahrenheit to Kelvin conversion. And you can see here I'm purposely doing floor division to mimic Python 2's way of doing division. And so typically when we write our functions, we write our function and we give it some values that we know. So we say, hey, convert Fahrenheit to Kelvin of 32, which is the freezing point of water. And we get 273.15. So that is, for those of us who have taken any chemistry, that's what we expect. And then let's say some other value that we know, the boiling point of water, 212 degrees Fahrenheit. And if we run that through our function, we get the same value back. And when we're testing our functions, that's usually probably what we do. We write our functions, we give it some variables, and we look at its output. And if it matches what we expect, then we think that we did it right. And so what went wrong here? Well, I told you this. I did floor division. We're actually supposed to do proper division and not just drop a decimal point. So if we fix that, we get the proper 273.15 and 373.15 as our values. So then we can say, hey, we're pretty confident that this function works. But just writing our functions and just looking at them visually, probably not the best way to do, especially when we work with larger software projects. So we want to automate this in some way, shape, or form. So at first, to make Dirk and everyone in Chicago happy, I will be talking about RUnit. So the way we run RUnit, I sort of just borrowed this or stole this from a post by John Miles White. I linked to it. If you guys go to this presentation, you can click it. But essentially, you write a function, and in this function, you use the RUnit, function, check equals. It will just compare two things, and if they're equal, return that it passed. Or if you're working with numeric values, you can say check equals numeric. And essentially, it gives it a value that you think is correct and the value that you are trying to calculate. And in this case, you save all your tests just so you separate your source code with your tests. You save it in a test directory. And in this example, we just give it a file name called 1.r. That's sort of the example John Miles White gives, and that's the example I'm showing you. And there's a reason for this. In RUnit, you really just look at two functions. There is a define test suite, which just defines all the tests that you're going to run, and then really a run test suite. So after you define test suite, you run a function that just runs it. There's two other functions that you don't really need, but they're also in the documentation, and they're helpful. And so how do we run RUnit? So on the top here, actually I should probably full screen this. At the top here, I load RUnit. I save the Fahrenheit to Kelvin function into a separate folder. In this case, I put it under src. And I save our tests in a file under the test folder. And so if we look at the f to k function, we get this. And if we look at our test examples, that's the function that we have. So now let's go actually run RUnit. So you define the define test suite. You give it a name. I'm just going to call it RUnit. You give it a directory for it to search for, in this case, the tests folder. And then you can give it a regular expression. So all of these files that match this expression, that's what it's going to run. So John Miles Wright gives an example of just give it a number, because you can just say 1.r, 2.r, et cetera, et cetera. You can define test suites that way. And then finally, you run your test suite. You can also print out the results of your test suite. So in this case, it's the test protocol. It'll give you the date and time you ran it, how many functions. In this case, it was one function, but it had two tests underneath. And you'll get that information. I really only had one test suite. It was only one file. That one file had one test, and there were no errors and no failures. And if you look down here, there were two checks. And those two tests that I made all passed. So I could have shown an example where I broke it and showed an output that had it failed, but this was 4 o'clock in the morning, and I guess I didn't think about that last night. So next package. Since we've pleased Dirk, let's anger him by talking about teststat, a package that Hadley wrote. So teststat, very similar thing, except this time, if you look at his documentation, he suggests putting your tests under a teststat folder under test. The reason for that is if you use some of the built-in dev tool functions, it'll actually automatically generate this folder structure for you. So I guess that's why you would do that. So I'm going to write a test underscore f underscore k or test temp conversion. So the way teststat works is very similar to nose in Python world, where it just looks for the word test in the beginning. If it finds it, that's what it's going to use. So that's the regular expression it's finding. So how do we use teststat? We load up the teststat package, and we define our test suite. So we say teststat. We can give this block of this test a name that makes sense. And then within these brackets, we just use the expect series of functions that come with teststat to give it input and outputs that we expect. And so the way we would write this, so this is actually, I just showed you, this is how you would write a test if you were in an interactive R console or something and you just want to run it. But if you want in a more formal way to just set up all your tests and run them all in one go, you can save all those, that test I just wrote. You can save it into a file, but the only additional thing you have to add is a context. So this is essentially saying that just give your test a name, just very similar to how RUnit worked. And so if we want to run this, we can load up the teststat library. We can source the folder that contains all of our functions, and then just run the testdir function that comes with the teststat package, and give it a directory. So in this case, teststat, and it will run all the tests and give you for each test that gets run, you'll see a period, and you can see in this case all my tests passed. So next thing I want to talk about is testing data. Who tests their data, or who tests their functions in R? Yeah, very few of you guys. So hopefully you fixed that. So data testing was something that I didn't know was a thing until I went to SciPy last year, and Eric Ma gave us a lightning talk about testing data, and that's something I've been thinking about ever since. So essentially, I just showed you how you test your functions, but you really want to make sure that you don't have a data set where you have pregnant males or something. that'll be a bad bit of data. So you want to make sure that stuff like that doesn't happen. Or if you're planning to take a log of a column, you want to make sure that there are no negative numbers, stuff like that. So just as a shameless plug, there is a epidemic going on in the world right now around Zika. And if you want, you can contribute or help parse data and contribute to the CDC repository. Yes. And so as I was working with this data, I sort of sent Michael Johansson from the CDC a bunch of issues on his repository saying that, hey, you sort of have a few problems in your data. For example, they had described that all your countries have to follow a country-state providence-city format. And for example, Haiti was missing the country. And a few other things regarding consistency with NA values, right? So I've been sending these pull requests, and sometimes I actually fix them, so I'm not just really complaining to the CDC. And so, for example, the Zika data, if you want, I stack them because at least they were good. They sort of learned their lesson, or not they, the world learned their lesson from the Ebola outbreak about having a centralized place for data. And so this time, working with Zika data is pretty nice because at least all the columns are the same. And so you can easily just R-bind stack them. So this is an example of what the Zika data looks like. And if you want, I built a Shiny dashboard for it. It's actually a really good training tool if you want to learn how to do modules in Shiny, if you look at the last 2 pull requests, but that's a little off topic. So the Zika data, all I do is I find all the CSV files that come from the CDC repository. I read them in using Hadley's package, and I just R-bind stack them all. And because I want the country, I just used the separate function from tidyr to break by the hyphen and rename that as country. So that's sort of what I did, and that's how I found the problem with Haiti, or at least people in my lab found the problem with Haiti. I didn't know that it was listing cities from Haiti. And so we have this data set that looks something like this, where we have country split and then the other locations. And so we can test our data. An example that you might do is, hey, you look at the country and you get a unique of that country. And so in this case, one of the problems was El Salvador was specified 2 ways. It was said in the documentation for the repository, no spaces, but there were cases where there had spaces between El and Salvador. And so one way you would visually try to inspect this is, hey, take a unique of the country, and if you get more than what you expect, that's probably how you would say, hey, there's something wrong with that column. Or you can take a unique and get a count of it. And so I expect El Salvador to just have 1 because that's what I expected. Or you can just do a table. So that's stuff that we probably do already during our data cleaning or visualization or understanding our data. So might as well just use what I just showed you guys and write a test for it. I realize I didn't show you an exact example of doing that because I'm going to move on to something else. But think about that. You've already gone through this process. You might as well just do a simple test to make sure that this happens. I've had cases where I renamed 88s and 99s as NA values and accidentally didn't realize that 88 and 99 were ID numbers in my data set as well. And it wasn't until very later on down the analysis when I was doing aggregate statistics that something didn't make sense. So if you find a mistake, write a test for it. It'll be great. Then you essentially just created metadata for your data set, and those 2 things can just travel and other people will know what's going on with your data. The last package I want to talk about is a package called Validate. So this is another way you can test your data. So you can use RUnit or test that to test your data using probably the standard R procedures that you've been using. But Validate is cool. It's kind of cool. You can install it on CRAN using install that package as Validate. And I'm really just going through a little bit of the vignette that they have to show this point. So there's really just a few things that you work with in Validate. You have a data set, you have a validator object, a confrontation object, or a confront. So essentially, you create a series of rules, and then you match, and then you take those rules and you confront your data with it, is essentially the process of what's going on. So how do we do this? So the example they use is the women's data set, which is really just 2 columns of women's height and weight. And so we can write a validation. where we can take the women's data set and we want to check that the height is greater than 0, the weight is greater than 0, and maybe just for this example, or their example in this case, height divided by weight is greater than 0.5, and then we can pipe it to their version of a summary. And you get something like this, where each row represents a test that we made. There were 15 rows in this case, and for the height greater than 0, all 15 of those matched. For weight greater than 0, all 15 of those matched. And for height divided by weight, 2 matched and 13 failed. And if you get other warnings or errors, it'll show up here. And then the last column is the actual expression that you wrote. So the way you use validate is you're actually just writing R code, and you're using that R code to validate your data set. So if you already know R, and you're doing these checks anyway, probably this is a nice way to have metadata travel with your data. It's a nice way to have metadata just travel along, and you'll always make sure that your data is correct. And so what we can do, instead of just showing the summary of it, let's just grab the actual validation object. And it comes with a nice bar plot function where you can actually plot how many for each of those rules passed or failed. So if you have a medium-ish size data set, you can run a series of validations and then just look to make sure that everything's green. Or if you see something that's, in this case, orange, or if you see a big block that's orange, it's probably something, you're probably making an assumption about your data that you didn't know about. And so another way you can validate data is using the validator function. In this case, it's nice because within validator, you can sort of create variables on the fly. So in this case, I'm calculating BMI on the fly. So this isn't me adjusting the actual data frame. I'm saying, hey, calculate BMI. It uses this := operator. Don't exactly know what that means, but that's what they use. And the equal sign itself doesn't work. So you can calculate BMI this way because you're converting from pounds to kilograms and inches to centimeters or something. So that's what's going on there. And then you're saying, we're running the same test: height greater than 0, weight greater than 0. And then let's just make an assumption that everyone's BMI is less than 23, or the mean BMI is between 22 and 22.5. And then you can run the same thing, but instead, this time, since you used a validator object, you use the confront verb, and you're saying, hey, for this given data set, women, confront it with our validation scheme. And if you run the summary, you get the same results back. Each row represents a validation or validation rule that you made, and you see how many passed and failed. And again, you can create a bar plot, and you'll see that me making an assumption that BMI falls between 22 and 22.5 is really wrong, or the average BMI is really wrong. And so that's it. That's my talk. You can find me on Twitter or GitHub, and/or livecoding.tv. I just gave a 3-hour Git intro on Wednesday for the data of intensive biology group at UC Davis. And yeah, if you want to find the slides, they're there. And I have 1 minute 30 seconds, so I can do free advertising, which is Hillary Parker here. Is she here? Hi. So Hillary runs a podcast called Not So Standard Deviations, and you guys should all be Patreon supporters and help her podcast. And if you do, you'll get a nice hex sticker. And she had said on Twitter that she will sign them. And since she's leaving New York, what a great present it would be to give her carpal tunnel because she shouldn't be leaving New York. And that's my spiel.